Hello, good people. How are you? And welcome back to Med Zone African Motives. Today, I want us to start on grade 10 physical sciences, looking into topics for term 1. We want to start diving deep into the topics that are made of what we refer to as term 1. So, in your term 1, according to your national ATP plan, which is your annual teaching plan, you are supposed to do a topic that we refer to as waves, sound, and light. So for your grade 10 physical sciences term 1, you're supposed to be looking into that topic. So before we can dive deep into waves, before we can start defining what sound is, before we can start looking into light, we need to start into our building blocks, which is our basics, which we refer to as pulses. So according to your syllabus, you are supposed to know what a pulse means. Mean to say that they will ask you to define what a pulse is. So a pulse is defined as a single disturbance that moves through a medium. Think of it as a single kick on a rope. For example, that picture that you can see there, you can see that maybe a friend of yours or you actually get to give a single kick on the rope. So you would see that the rope will start oscillating. So this just single short disturbance or displacement, this single kick that you can see here is what we refer to as a as a pulse. This single disturbance is what we refer to as a as a pulse. At some point in time you might think of it as a ripple when it comes to water. Let's say, for example, you drop some water into into a pool of water, or else into a bucket of water. You start seeing some ripples. So that single ripple that you see in your water is what we refer to as as a pulse. That is what we describe as as a pulse. It is a single disturbance that moves through a medium. Now that we know what a pulse is, we now need to define what we refer to as a medium. What is it that we refer to as a medium? Because we have defined our pulse as a single disturbance within a within a medium. So what is a medium? I would like to say that medium is just a fancy word that describes stuff like water, your rope, or else your air. This is a substance or material through which a pulse moves. So, like we said, that if you drop a single drop into water, you would see that you would start seeing some ripples forming. So we would call that the water is what we refer to as as the medium there. And then if you were to shout, you would actually hear some echoes within your surroundings. Let's say that you were in mountainous areas. So we are saying that the air itself is the medium, because it is material or else a substance through which the pulse is moving. Or else, if you were to actually get to give a single kick or else a slinky on on a rope, you would see that the rope is the one that is going to be displaced up and down. So we are saying that the rope becomes our medium through which our pulse is moving. So you know that the medium does not create the pulse, but at some point in time, it is you who created that pulse. The pulse is just moving through a rope. So the rope becomes the medium in which the pulse moves through. It does not create the pulse itself. Or else you look into your water, the water does not create the ripples, but the drop that you dropped in that water. Or else, let's say, if you were having a pipe of water, or else, let's say, just a pipe in the in your pool of water, and then you get to sling it, you would see that there will be ripples around that pipe. Or else, let's say you are trying to drain water from your pipe, you would see some vibrational ripples around your draining pipe. So we are saying that the water itself is not the one that is creating those ripples, but the ripples are being created by the what? By the vibrations that are what? That are coming from a what? From the pump that is draining that what? That is draining that water. So what I'm trying to say is the medium does not create the pulse, and the medium is not the pulse. But however, you would know that in each medium, the particles that make up the medium are going to be temporarily moved from their rest position. That is why you would see some ripples on your water. You would see that the water particles have been what? Have been moved due to the vibrations. And also here, the rope has actually been moved up and down due to that what? That single kick that you gave that rope. So we are saying that the medium is actually the particles that carry your pulse, but they do not create the pulse and they are not the pulse. But the particles within the medium are just going to be temporarily moved from what? From their rest position. So where are we driving with this? We are saying that within a pulse, you would see that we describe two different types of pulses, where we have got transverse pulses, and then we have got what? Longitudinal pulses, where we would describe them in terms of the movement of the what? Of the particles within the media. But before that, I want us to look into the parts of a pulse. We said that a pulse is just a single disturbance, is just a single disturbance within a medium. So you would see that within a pulse, you would be having what we refer to as a crest. And we are saying that the crest is the highest point of a pulse. And then you would also have what we refer to as a trough. So a trough, just think of it as the lowest point. So think of you going uphill and then later going downhill. So a crest, we will call it the what? The top of the hill, whilst the trough becomes the bottom of the hill. So the crest becomes the highest point of a pulse, and then the trough now becomes the what? The lowest point of a what? Of a pulse. And then we have got something that we refer to as the amplitude. The amplitude becomes the total displacement, or else the total distance within which the particles of the medium would be displaced from their position of rest. So this line represents the position of rest. And then since we can actually relate from how our rope was actually kicking, you would see that the particles of the rope would go up the hill and then come back. So this distance from this position of rest up until to the top of this crest is what we refer to as the amplitude. And the amplitude actually determines the amount of energy the pulse is carrying. So the greater the amplitude, the greater the energy that the pulse is carrying. And then we have what we call the rest position, or else the point of equilibrium. This is the line within which your medium particles would be if there was no disturbance. And then we would actually come to define something that we refer to as the what? As the pulse length. The pulse length, this is the distance between the start of your what? The start of your pulse and the end of that pulse. So the distance in between the start and then as we go up and then the finish, or else the end of the pulse, is what we refer to as the what? As the pulse length. So these are the parts of a what? Of a pulse. So you might be asked to define or else to state the parts of a what? Of a pulse. And then now, since we now understand more and in depth about what we refer to as pulses, we now want to describe or classify our pulses. So we've got two types of pulses. We have what we refer to as transverse pulses. So transverse pulses, this is where the disturbance is up and down while the pulse moves forward, like the one that you would get when you actually get to have a what? A kick on your rope. So you would see that the pulse itself is moving towards the right. But however, the particles of the rope are disturbed what? Up and down. It means that they are displaced from the rest position and then they go up and then they later come down. So this is when a disturbance goes up and down while the pulse is moving what? Forward. So we get to say that the particles of the medium are displaced perpendicular to the what? To the direction of the pulse. So when we say perpendicular, we say that there is a 90-degree angle between the direction of what? Of displacement of your particles of the what? Of the medium. So these are the particles of the medium, whilst the direction of your what? Of your pulse is moving in that direction. So there is a 90-degree angle between the direction into which the particles of the medium are displaced and the direction into which the pulse is moving. That is what we refer to as what? As transverse pulses. And then what we refer to as longitudinal pulses, this is when the disturbance is back and forth along the what? The direction is the movement of the what? Of the pulse. This, I'm sure you can find it when you actually get to what? To stretch and compress a spring. Think of a spring. When you actually stretch it or else compress it, you would see that when you stretch it and then you release, the spring itself, the particles of the springs, they move back and forth, while the pulse movement is actually going what? Along the horizontal direction, or else along the same movement as the what? As the movement of the spring. So that is what we refer to as the what? As the longitudinal pulse. We get to say the particles are displaced parallel to the movement of the pulse. So we are saying that one example of a transverse pulse, we call that a flicking of a rope. So an example in which you would give, they would say, give an example where you would actually get to what? To define a transverse pulse. You can say flicking a rope, flicking a rope. And then give an example where you would find longitudinal pulse, a push in a spring. A push in a what? In a spring. That is what we refer to as what? As transverse and longitudinal pulses. Now, when it comes to pulses, there is a principle that governs the behavior of what? Of our pulses. Like, for example, whenever we have got two pulses, and those two pulses, they are acting in opposite direction, and at some point in time they get to meet, there is a principle that we can actually get to refer to that tells us how these two pulses they will interact. And that principle is what we refer to as the what? As the principle of superposition. So the principle says that the principle of superposition, it states that whenever two disturbances occupy the same space as shown below, at the same time, the resulting disturbance is the sum of the two disturbances. So we are saying that if we have got this disturbance and then we have got that disturbance, and these disturbances, they get to occupy the same space at the same time, the resulting disturbance would be the sum of these two disturbances. Meaning to say that at the position where they meet, the resulting disturbance will be the sum of these two. Meaning to say that their amplitude is going to be the sum of the two amplitudes that we see here. That is what the principle of superposition states. So in summary, we can say that whenever two pulses meet, they add up. So this is where now we now need to actually get to define what we refer to as what? As constructive interference or interaction, as well as destructive interference or interaction. So you would see that what we refer to as constructive interference is when two pulses meet and there is a resulting bigger what? Pulse. So we are saying that whenever two pulses meet and they result in a bigger pulse, we call that what? Constructive interference. So this is when we have got a pulse that is having its crest moving towards the right, and a pulse that is having its crest moving towards the what? Towards the left. And then these two pulses, they get to meet. When they meet, they would have their amplitude being equal to the sum of the two crests, as you can see here. So you would actually get to see that the example that I brought to you here from the picture that you can see, we have got a pulse that moves towards the right and a pulse that moves towards the left. And then these two pulses, they intermeet, or else they constructively interfere, and then they actually get to form a what? A bigger amplitude, or else a bigger pulse. And then after their interaction or their interference, they actually get to move away from each other with the same amplitude that they were having. So this is due to what we refer to as the what? As the energy conservation law. So our energy conservation law takes play to actually get to tell us that energy is neither created nor destroyed. Meaning to say that the same energy that our pulse that was moving towards the right was having is the same energy that it will have after this interference. It will continue moving to the right with the same amplitude. And then this one, which was moving to the left, it will continue moving to the left with the same amplitude. But when these two interfere, they would actually have a what? They would have a double amplitude, or else the sum of these two. The same as whenever two troughs, or else whenever a pulse having a trough is moving towards the right and a pulse having a trough moving towards the left, they interfere. They would actually have their amplitude being the sum of these two troughs. So they will be having a what? They would be having a double negative amplitude. So if we are to take this one as positive amplitude, this one would be double, being on a positive direction, whilst this one would be double, being on a negative direction. So we are simply saying that the resulting pulse would be having a what? A bigger, or else a greater amplitude than the two. That is what we refer to as a constructive interference. And you have to take note that we said that these interferences, they are governed by the what? By the principle of energy conservation. Now let's look into destructive interference. So when it comes to destructive interference, we are now saying that this is the opposite of what? This is the opposite of constructive interference. So we are saying whenever two pulses meet, they would actually get to what? To result in a smaller pulse. So what is it that we mean? We are saying, let's say for example, we've got a pulse that is moving towards the right and it has got a crest, and then we've got a pulse that is moving towards the left and it has got a trough. When these two interfere, they are actually going to cancel each other if they are having the same amplitude in different directions. Meaning to say that we have got a same positive magnitude and a same negative what? Magnitude. They are going to cancel out. But however, if let's say the other one is bigger than the other one, we are going to have a what? A decreased amplitude, like this one. Let's say this one, the displacement here maybe was 5 centimeters, whilst this one, because it's in the negative direction, the displacement was negative 3 centimeters. It simply means that the resulting pulse after interference would be having an amplitude of what? Of 5 plus negative 3, which is just equal to positive 2 centimeters. So our resulting amplitude there would be a positive 2 centimeters. So that is what we refer to as the what? Destructive interference and constructive interference. So those are the characteristics of what we refer to as what? As pulses. Now, just to check on our comprehension, if we understood what we were saying, or else if we now have an idea of what is referred to by a pulse, by a medium, as well as constructive and destructive interference, Let's look at this example that I brought you here. They are saying that the two pulses shown below approach each other at 1 meters per second. Draw what the waveform would look like after 1 second, 2 seconds, and 5 seconds. So before we can actually get to attempt that one, I want us to define something. There is something that we refer to as speed. Speed will always be the same. Either we are looking into pulses, we are looking into motion in one dimension, or else we are just looking into what? Into general motion. Speed is just given by the what? By the total distance traveled divided by the unit time taken to travel that what? That distance. So you know that your speed will always be distance over the what? Over the time taken to cover that what? That distance. So it will be given in what? In meters per second. It will be given in meters per second. That's your speed. So if you have got your speed, you would know that it is distance per unit time. So here we have been given the speed of our pulse, and then they are saying that draw a waveform that would be formed after a time period of 1 second and 2 seconds and 5 seconds. So they are just giving us our pulses in terms of our speed and in relative to the what? To the time that it would have passed. So don't be confused there. Just try to make sense of whatsoever that they are saying in regard to the principles that you know and you understand from either mathematics or else from combined science. Now, if that is said, let's look at this example. So now we can see that we have got pulse A and pulse B. And pulse A is actually in between what? In between the distance of 2 to 3 meters. As well as pulse B is in the distance between 6 to 7 meters. And then they are saying that this pulse is moving at 1 meter per second. So after every 1 second, we are moving what? 1 meter. And they are saying after 1 second, what would the waveform look like in between A and B? So the simplest, let me say that the simplest idea that I can give you there is to come and draw the same graph that you are given there. So let's say here, this is where we are having our 1 meter, our 2 meters, our 3 meters, and our 4 meters. And then here we are having our 5 meters, we're having our 6 meters, 7 meters, 8 meters. They are saying this is in progress of the what? Of the distance moved in meters. And then this side, this becomes our amplitude. So there it would have been what? So let me say this is amplitude A, and then this is the distance moved. Right. So since initially our wave, our pulse, sorry, is actually in between 2 and 3. After 1 second, it would have moved 1 meter. So it would be moving from 2 to 3. So it will now be starting here, and then it would be ending at what? At 4. So you would be having your pulse with the same amplitude. So that is what it will look like after what? After 1 second. And then for B, so this is A. And then for B, initially, it is in between what? 6 and 7. And then it is having an amplitude of 1. And then after 1 second, it would have moved what? 1 meter. So 7 will now be at 6 and 6 will now be at 5, because we are just moving the start point of this pulse to be at 6 now, and then the end point to be at 5. So now we will now be having what? We will now be having B starting at what? Starting at 6, because this is 7. and ending at what? At 5. But mind you, it will be having the same what? It will be having the same amplitude because there is no interference there. That is B. And B will simply be moving towards the left, whilst A would be continuously moving towards the what? The right. That is after what? After 1 second. That would be the result after 1 second. Now, what about after 2 seconds? Let's go hand in hand now. We'll continue with the same drawing. Let me just get to bring the same drawing down there. I just want to make sure that you get the depiction of whatsoever that is happening here. So maybe you would allow me to just get to rub off that, because you now know that below there we are representing what? Distance. Now, if that is the case, let's say that this is our reference point. Yes. And then we are still having 1 meter as our amplitude and 2 meters. So this was 1 and this was 2. This is 1 and this is 2. This is 1, this is 2, 3, 4, 5, 6, 7, and 8 in meters. This is our distance and that is our amplitude. Now, let's look at our motion after what? After 2 seconds. So after 1 second, these pulses, they moved what? A distance of 1 meter, a distance of 1 meter. Now they would move a distance of what? Of another meter, because now it's now after 2 seconds. That is, they would have moved a distance of what? Of 2 meters. So 2 meters from 2 would be equal to what? It would be 2 unto 3, it's 1 meter there. And then there is another 1 meter. So when we were starting at 2 meters there, for A, we are now starting at what? At 4 meters. Where we're ending at 3 meters, we are now ending at what? At 5 meters. That is for A. Because now it has moved a distance of what? It has moved a distance of, let me just correct that. I want to correctly represent it. It has now moved a distance of 2 meters. This was 1 meter. Now it has moved a distance of 1 meter, 1 meter. That is 2 meters after 2 seconds. Now the pulse is now here. Let's say that this is where the pulse is now. Now, let's look for this. Let's look at this one as well. Let's look at B as well. So I just want to rub there. And then I would actually want to say that for this one, it moved a distance of 1 meter from this side to that side. Now, it has now moved 2 meters. So it would have moved 1 meter, another 1 meter. So it simply means that now it is starting at what? At 5 as well, having an amplitude of what? Of 1 meter, and ending at what? At 4, having an amplitude of 1 meter. So that is how you would have it. So these two, they will now get to what? To interact in between 4 and 5 meters. So that is where we are going to have what? A constructive interference, because these two, they are having what? A crest and a crest. So we are going to sum this amplitude of B, let's say B1, and this amplitude of A, A1. If we add A1 and B1, this is what we this is what we will get. We would say 1 meter plus 1 meter, and then we'll get what? An amplitude of 2 meters. So after 2 seconds, this is how the waveform would actually get to what? To look like. And then what about after 5 meters? What about after 5 meters? Now let's continue with our drawing. We will just get to do the same. We have got 1 there, and then we have got 2 there, and then we have got what? 3 there, we have got 4 there, we have got 5 there, we have got 6 there, 7 there, and 8 there. And then let's get to have that, and we are saying that this is our reference point. And then, or else that is the point of rest. That is 1 meter, that is 2 meters. And then that is 1, 2, 3, 4, 5, 6, 7, 8. Now, let's look at pulse A. It is now after 5 seconds, it would have moved what? 5 meters, because we are saying the speed is equals to distance over time taken. Now the speed is what? The speed is 1 meter per second, and then the time taken is what? We are saying that the time taken here, it's now 5 seconds. So the distance there would be speed times time. That is 1 times 5. So it would have moved the distance of what? Of 5 meters. This is the same with the here. The distance would be speed times time. We would actually get to say 1 meter times 2. It would be 2 meters. That's the reason why we said this one moved 1 meter or 2 meters this side, 2 meters this side. Now, if I'm to say this moves 5 meters, it would actually get to say from here to move 1 meter, and then 2 meters, 3 meters, 4 meters, and 5 meters. So it simply means that now this is where it is. This is where it is with the same amplitude. So you can see that after interference, you would be having this. This is what you are going to be having. Your wave would, your pulse will continue moving with the same speed, with the same amplitude. So this is now A. After what? After 5 seconds. And then now let's look at what? At B. B started where? B started here. So B would have moved what? 1 meter, 2 meters, 3 meters, 4 meters, and 5 meters. So it simply means for B also, you would be having B here, because B has moved this 5 meters. So now you would have your B in between 1 and 2. So that becomes B. And B would still continue in the same direction with the same amplitude. So that is simply how we were supposed to interpret that. And that is simply what we refer to as pulses. So now I just want to show you the clear diagrams, and then the answers that were coming from the textbook where I took that example, so that you can see exactly how they wanted you to represent it. So they were saying that after 1 second, pulse A would have moved what? 1 meter to the right, and pulse B would have moved 1 meter to the left, just like we represented it, to say that since it was from 2 to 3, now it will be from 3 to 4. Since it was between what? 7 to 6, now it will be what? 6 to 5. And then after 2 seconds, they would actually get to interact or interfere, that is to meet in between 4 and 5. They will meet in between here. So if we move another second, it means that we've moved another 1 meter. So when they move another 1 meter, these two are going to what? To interfere. So we are going to add A and B. What we are adding between A and B is their amplitudes, so that we end up having what? An amplitude of what? Of 2 meters. And this is what we refer to as what? As constructive interference. This is what we refer to as constructive interference. And then thereafter, now they're saying after 5 seconds. So now you know that A started between 2 and 3. So he will now move 5 meters after 5 seconds. That is 1, 2, 3, 4, 5. So it is now between 7 and 8. And then B started between 7 and 6. It will now move 1, 2, 3, 4, 5. So it is now between what? 2 and 1. So that is what we refer to as pulses, and that is the example that I had. So I'm sure and I'm hoping that now you have got an idea of what we refer to as a pulse. You can be able to define a pulse as a single disturbance that occurs through a certain medium. And you would know that the medium does not create the pulse, nor does the particles of the medium actually what? Become the pulse. But instead, the particles of the medium are just temporarily displaced and then they come back to position. And you now know how to define a transverse pulse and a what? And a longitudinal pulse. So let's meet in our next video when we now start defining what we refer to as a wave. When we are now starting to build what we refer to as a what? A train of pulses. When we have got many consecutive or series of pulses, what is it that we are going to form? Let's say, for example, you have got a series of pulses like this. What is it that you are going to form? That is what we now want to look into. So let's meet in our next video. I hope you understood. Thank you.